Hello everyone. Last time we have discussed about Einstein's explanation of the photoelectric effect and its laws. So Einstein proposed an equation called as Einstein's photoelectric equation, on the basis of which he explained all the laws of photoelectric effect accurately. Today we will at the first verify the Einstein's photoelectric equation, and then we will proceed towards the D-Broglie hypothesis of dual nature of the matter. So let us start. So Einstein photoelectric equation, it is given by this equation, as you can see here. The kinetic energy possessed by a photoelectron after getting emitted out from the metal surface, it is given by h nu minus h nu naught. Here h nu naught, it is nothing but the work function of the metal, and h nu is the energy of the radiation, or we can say photon, which is incident on the metal surface. Of course, this h nu, it should be more than h nu naught. Only then the electron will be emitted out, or this can be equal to h nu naught, but it cannot be less than h nu naught. Otherwise the kinetic energy will come out to be negative, which we already have discussed that is a not possible case. Okay, so we also know that this kinetic energy of the emitted out photoelectron, it is also calculated or known by the stopping potential which is required to stop it, which is which is V naught, for example. So therefore kinetic energy, it is also measured from the stopping potential. So the kinetic energy of electron is also written as E V naught, where E, it is the charge on the electron, and V naught is the stopping potential or the negative potential required to stop it from reaching the anode, right? Okay, so both of these equations talk about the kinetic energy possessed by a photoelectron. So we can equate them, and on equating we get this expression, and from here we get V naught, the stopping potential. We are taking E, the charge on electron, to the other side. So this is the equation we get here. So it is the equation which relates the stopping potential to the frequency of the incident radiation. All other factors are constant, whether it is nu naught, the threshold frequency, h, the Planck's constant, or E, the charge on the electron. So it is the relationship between just the stopping potential and the frequency. From here, to make it slightly more easy to understand, we are taking h upon E to be common. So inside we are left with only nu minus nu naught, right? So here h upon E is constant, nu naught is constant, so it is the relationship between just V naught, the stopping potential, and the frequency. Millikan made use of this equation and plotted a graph based on his experiments. He plotted the graph between the frequency nu and the stopping potential V naught, and the graph was found to be just like this, which is a inclined line just like this. So along the vertical, it is either the stopping potential or the kinetic energy, and along the horizontal, it is the frequency. From the graph, we already know that this point where this graph meets the frequency axis, the point where this graph cuts the frequency axis, it gives the threshold frequency, below which there will be no emission, right? So this we already know about it. Now we compare this equation, this here. I am comparing this equation with the this equation, which is the equation of a linear equation of a straight line. So whenever we compare both of these two equations, this is the general form of the equation. We see that in place of m, we have here in this equation h upon E, and C is something which is constant. So it is h upon E nu naught. It is already constant because each and every term here it is constant. So m is nothing but here the slope. So that means slope of this graph, it will be m, which is known to be h upon E here. We need not to calculate h upon E here. Here whatever the slope of this graph will be, it will be h upon E, right? So what Planck has did, he measured or calculated the slope of this graph mathematically, and because it is already known that the charge on electron is E 1.6 into 10 to the power minus 19 coulomb. So by knowing h upon E, he equated this ratio h upon E to the value of this slope, because h upon E is nothing but the slope, and substituted for the charge on the electron and calculated the value of h, the Planck's constant. He found that the value of h was quite accurate as known. Okay, then he calculated the value of work function by multiplying this ratio h upon E with the threshold frequency, this, right? So whatever the value has come for the work function, it was very close to the actual values. So Millikan, however, tried to disprove the Einstein theory of quantum nature of the radiations, but his experimental and theoretical explanation, instead of disproving, just proved the Einstein's photoelectric equation and quantum theory of radiations, because what the value he has calculated about Planck's constant and work function, they were quite close to the actual values. So in this way, the photoelectric equation has been established, or we can say verified. So photoelectric effect, which we have discussed here, has very wide applications, just like this. You can read them. Okay, so we have discussed about dual nature of the radiations. So in this we have discussed that wave theory of radiation proposed by the Huygens, it explains the phenomena of interference, diffraction and polarization in addition to the phenomena of reflection, refraction and so successfully and clearly. But the same theory, wave theory, does not explain the phenomena just like photoelectric effect, Compton effect, black body radiations, X-ray spectra, etc. Right? So that means considering wave can explain only the effects of radiation just like interference, diffraction and polarization. But considering light or radiation as a wave cannot explain the phenomena just like photoelectric effect, Compton effect and black body radiation. That means during one kind of phenomena just like interference, diffraction or polarization, light can be supposed to be behaving just like a wave, and on the other hand, when the phenomena just like photoelectric effect and Compton effect and black body radiation etc. are taking place, then the radiation can be supposed to be behaving just like the quanta of energy, means particles. So therefore radiation have dual nature. But one point here to remember is that during one kind of process, the light can behave only in one way, either in wave nature or in a particle nature, right? So dual nature cannot exist, dual nature of radiation cannot exist simultaneously. At the same time, a radiation cannot possess both kind of behaviors. So there is no experimental evidence where the radiation can behave as a wave, as a particle on the same time. Okay, so that is about the dual nature of the radiation. Loius D-Broglie, he was of the idea that if radiation can have both kind of characters just like a wave and particles, then the material particles can also possess both kind of the behaviors as the particle as well as the wave. So he made his suggestion based on the hypothesis that in this universe nature loves symmetry. In this universe everything is in symmetry, symmetrical situation there exists everywhere in the nature. And the second, he said that the universe is made of particles and the radiation, means mass, everything in this universe exists in the form of the mass, material particles and the energy, or we can say radiations, and both entities must be symmetrical. So based on this hypothesis, he put forward that the material particles should also behave just like a wave and as a material particle, just like the radiation does. So D-Broglie said that there can be a wave which can represent a moving particle, right? Which can guide the motion of a moving particle. So we can take there a wave which is associated with a moving particle always, and this wave associated with moving particle are called as the matter waves, or in the honor of D-Broglie, Loius D-Broglie, they are also called as the D-Broglie waves. So it is simple, according to D-Broglie, that there can be a wave which can clearly guide them, or we can say establish the motion of a moving particle, and this wave is associated with the material particle. It is called as a matter wave or a D-Broglie wave. He also gave a method to measure the wavelength of this wave associated with the material particle, called as D-Broglie wave or the matter wave. According to that derivation, quantum theory says that the energy of a photon is given by E is equal to h nu, and because nu, the frequency of photon, it is written as c upon lambda, so energy of the photon is written as hc upon lambda. And there is also Einstein's theory regarding the energy of photon, which says that if m is the mass of the photon, then its energy will be given by E is equal to mc square. This is the mass energy equivalence. So both of these equations are talking about the energy of a photon. So both can be equated. So from here, when we equate these two equations, we get the wavelength associated with the photon. So this wavelength comes out to be h upon mc. Here m is the mass of the photon, which is not the rest mass of the photon, because rest mass of photon is 0. So okay, so m is the mass of the photon, which is a packet of energy, and c is its speed. So m mass into speed, which is nothing but the momentum of the photon. So therefore lambda can be written as h upon p. Means the wavelength of the photon associated with a photon, it is, according to D-Broglie hypothesis, it can be written as h upon p. But instead of this photon, if we have a material particle of some mass m which is moving with some velocity v, right, then the same equation can be written as lambda is equal to h upon its momentum. Here it was m into c, now it is m into v, because the particle, it is moving, material particle, it is moving with velocity v. So this is the expression for calculating the wavelength of the D-Broglie wave, or we can say matter wave associated with the material particle. So from here, on the basis of this discussion and expression, we can conclude that the D-Broglie wavelength is inversely proportional to the velocity of the particle. That means a faster moving particle will have a shorter wavelength and vice versa. And we also conclude that a heavier particle will have a shorter wavelength. And also we can conclude that if a particle is at rest, that means its velocity is 0, its wavelength will be infinite. That means such a wave will not be observable. From here, it can also be concluded that D-Broglie wavelength, it is independent of the charge of the particle, right? So that means each and every particle, whether it is charged or not, it can have the D-Broglie wave associated with it. There are two more important facts regarding these D-Broglie waves or matter waves, which are necessary to understand or keep in mind, that these matter waves can travel in vacuum just like the electromagnetic waves can do, and hence they are not mechanical waves. The first thing is that matter waves are not mechanical waves. They can also travel in vacuum just like electromagnetic wave, but matter waves are not electromagnetic waves in nature, because they are not produced by accelerated charged particles. So these points must be remembered. These matter waves or D-Broglie waves are probability waves. So they are called as the probability waves because the amplitude of the wave gives the probability of existence of the particle at the point. Where the amplitude of this D-Broglie wave or matter wave associated with this moving particle, amplitude is maximum at that point or in that region. the probability of finding the particle is maximum, right? Okay, so let us proceed ahead. On the same steps, we can calculate the wavelength associated with the matter wave of an electron, moving electron. So for an electron of mass m and charge E, when it is accelerated by some electric potential V volts, then its energy can be written as E is equal to E into V, where E is the charge on electron and V is the potential by which it is accelerated, right? So when a charged particle just like this electron, it is accelerated, so it possesses all of its energy due to its motion, called as the kinetic energy. So the energy of an electron can be written as half mv square, where v is the velocity with which it is moving. So from here we can calculate the expression for the velocity of this electron, which is 2e upon m under the root, right? And we already know that the De-Broglie wavelength of a material particle, for example, if we are talking about electron, it can be written as lambda is equal to h upon mv, where m is the mass of electron and v is its velocity. So when we substitute the value of v from here to here, then we get the lambda, the wavelength of the wave associated with a moving electron. It is equal to h upon 2me under root. On solving, substituting for v and then solving, we get this expression for the wavelength. So this remains the formula for the wavelength of an electron, moving electron, wavelength associated with a De-Broglie wave associated with an electron. So we can also put the value of this energy possessed by an electron to be E into V. So this is another form of the finding the wavelength of an electron. So here all terms, Planck's constant h, the mass of electron m, and charge on electron E, all these are constants, right? So on substituting the value of all these, we can write the general expression for the wavelength associated with an electron to be 12.27 divided by root of V. This V is nothing but the accelerating potential. So whatever the wavelength, what is the wavelength of electron? It will depend upon by which potential it has been accelerated. So if it is 100 here, so that means simply the wavelength associated with the electron, it will be 1.227 angstroms. In similar steps, we can calculate the wavelength associated with any material particle, whether it is charged or not. Only the thing is that we should be knowing its energy and its mass. Okay, so Devison and Germer has performed an experiment to check the existence of this De-Broglie hypothesis. So for this, what he did, he performed an experiment. Devison and Germer, they were two scientists, physicists. He created an electron gun which is heated upon by some voltage, which can be increased or decreased. So here is a filament which when heated upon, it starts emitting out the electrons, and these electrons are made to move towards one particular direction. So therefore this system just creates an electron gun. So the beam of these electrons is made to fall on a particular we can say nickel crystal, for example, which is cut along the cubical axis, so that the planes of the nickel crystal are just like this. They can be at any angle. So this incident electron beam is now incident on this nickel crystal. So from these the planes of this crystal lattice, the electron beam is getting scattered, or we can say diffracted, all over the directions. These scattered electron beams are received by a detector which can rotate at any angle in order to receive these scattered electron beams. Energy of these electrons which are emitted from this electron gun, this can be increased by increasing the potential here, right? So this is the accelerating potential. In other way we can say that. So this the velocity of electron gun, or we can say the energy of electrons, can be increased by increasing this potential, accelerating potential. So two important observations has been made here about these scattered electrons. The graph has been plotted between the incident beam and the intensity of the scattered beam at different values of accelerating potential. It has been observed that the pattern of the scattered electrons is very similar to the X-ray diffraction pattern, right? So if it is the pattern is quite similar to the diffraction pattern of the X-ray diffraction as explained in Bragg's diffraction, X-ray diffraction, then the point is at what point is the amplitude or intensity of the scattered beam is maximum and in what situations. So it has been observed that the intensity of the scattered beam is maximum at the scattering angle 50 degree and at the accelerating potential of 54 volts. For all other accelerating potentials, the intensity of the scattered electron beam is comparatively less. So 2 points here has been concluded or observed, important facts. So intensity of the what are these points? That the intensity of scattered beam of electron is found to be highest when angle of scattering is 50 degree, right? And the accelerating potential is 54 volts. So from these observations, the D-Broglie wavelength has been calculated by two methods. One that has been proposed by D-Broglie hypothesis and other one by the Bragg's equation. Because if in this electron scattering, if electron diffraction is similar to the X-ray diffraction, that means here we can apply the Bragg's equation also here. So let us try to find out the wavelength associated with this electron beam, scattered electron beam by the first method of Bragg's equation. So here we see that this angle theta in Bragg's equation 2d sine theta is equal to n times lambda. Here d, it is the lattice spacing, the spacing between the planes of the crystal lattice of the nickel. Theta, it is the glancing angle, right? The angle made by the incident beam of the electrons with the planes of the crystal lattice, and n is the principal quantum number. So here glancing angle, this phi, the angle of scattering, we are calculating it for the maximum intensity of the electron beam. So we found it to be 50 degree, right? We found it to be 50 degree, right? So these two angles, considering all these factors, we can calculate this glancing angle, which is theta here, to be 180 degree. So this theta comes out to be 65 degree. Substituting the value of all these three angles, the sum of all the angles will be 180 degree. From here theta comes out to be 65 degree. So this is the glancing angle which we can substitute here. And also because we are using the nickel crystal, so the crystal spacing between the crystal planes is 0.91 angstroms. And for first principal quantum number, n, the value of n is 1. Substituting for d, theta and n, we can calculate the lambda, and it has been observed in the experimental facts that the wavelength associated with the electron beam, it has come to be 1.65 angstroms. Okay, so this is the one way in which the wavelength has been found. On applying the D-Broglie hypothesis, because the same intensity of the electron beam, which is the maximum intensity of the electron beam, it is observed at the accelerating potential of 54 volts. So we have to calculate the wavelength of this D-Broglie wave associated with these electron beams at this accelerating potential of 54 volts. So in the expression of the wavelength, we are substituting the value of V to be 54 and making calculation. We see that the values of the wavelength, according to D-Broglie hypothesis, it comes out to be 1.67, which is very close to value what is known by the this Bragg's equation. So two values are very close to each other. That means the diffraction pattern of electron scattering and the Bragg's X-ray diffraction is quite similar, and therefore we can suppose a wave to be associated with the scattered electron beam. So electron beam is showing the diffraction pattern very similar to the X-ray radiations. So that means electron beam also porous electrons, which are the material particles, also shows the wave-like character. So in this way, this is the graph showing the variation between intensity and the potential, accelerating potential. So it has been observed that the intensity of the electron beam was found to be maximum when the potential was 54 volt. You can see here the diffraction pattern for different number of electrons. So we see that the diffraction pattern is very similar to just like the diffraction pattern in case of X-ray diffraction by the Bragg's equation, and hence that establishes the dual nature of the matter waves also. So that means according to D-Broglie hypothesis, if radiation can behave as a wave as well as particles, then the material particles can also possess both kind of properties, just like a wave, just like a we can say material particle. But in one kind of phenomena, it will have only one kind of character. That's it. Thank you.